In today's video, you are going to learn how to run a paired samples t-test in R. To start, let's review what a paired samples t-test is. If you have not watched the videos about independent samples t-test yet, I recommend going back and looking at those videos first. In these videos on the paired samples t-test, I'm going to go a little bit faster because some of this should be review now. Just like we talked about last time, a paired samples t-test allows you to look for the difference between two performances by the same group. In your workflow, first, we'll check our assumptions, then we'll run the test, and then we'll interpret the results. Remember though that you would also do an item and reliability analysis, and you would report your results if you were researching this in a real environment. First though, we need to import our data. Go ahead and make a new heading called Paired Samples T-Test. Import your data. And then follow through with this code. You'll see that it is exactly the same code that we used before doing the independent samples t-test. So it's an option for you to copy and paste that code, but you need to change your variable names. It's important to change your variable names because we're working in the same document, and if you keep your variable names the same, it can be, number one, confusing, and number two, it will change the variables that you made before. So you want to keep all your variables in good shape, so you want to change them. I've changed independent to PRD for paired. So you change it here, 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 and paired and paired. Now let's run this code line by line. First, we find our data set, and it needs to be in a CSV format. Here's paired sample t-test. So we've imported it, and now we can take a look at it. Remember that these data are only for educational purposes, and you should not take the results that come out of them too seriously. So they're just for learning purposes. What these data represent, imagine a study, and these are the scores on a pre-test and post-test from an experiment about the effectiveness of recast as implicit corrective feedback. So here's our pre-test before the experiment was conducted, and here's our post-test scores after the feedback was given. I will explain what this column means in a moment. Now let's make some descriptive statistics using the summary function and take a look at them. Whoops. And now we'll take a look at them here. And you can get a sense of what the data look like, what your means and median is. Now that we have those variables in our environment, let's move on to our assumptions. You'll see that assumption number 1, number 2, and number 3 are the same as before. I won't go over these because we went over them with the independent samples t-test. Assumptions after 1 through 3 are different though. You'll see that there's only one more assumption, and the assumption is that your dependent variable should be approximately normally distributed for each group of the independent variable. So this looks similar to what we saw when we did the independent t-test, but in the paired samples t-test, the assumption of normality and no outliers is tested on the differences between the paired values, not the values of the paired groups themselves. Remember this column here? We've gone ahead and added this column that is the difference, which means column A minus column B equals this. Or vice versa. It can either be A minus B or B minus A. That gives us our difference, and we use these values, the difference, in order to look at whether our data are approximately normally distributed. You would have to do this. You could either do this in R itself, in RStudio, but it might be easier just to do it in whatever spreadsheet you're working in before you import your data, like we did today. Next, we want to make a box plot and take a look at the box plot. Just like before, here's our function for box plot, and we just want to take the column difference. Looking at the box plot, we can see that there are no outliers. There are no outliers that would be okay, and there are also no outliers that are extreme and that we'd have to do something with. Next, let's take a look at our Shapiro-Wilk statistic. The Shapiro-Wilk statistic, the important value here is the p-value, and we can see that the p-value is greater than 0.05, which means that our data are indeed normally distributed. Now, let's move on to running the t-test now that we've passed our assumptions. The code for running a t-test is very similar to what you saw running the independent samples t-test. The main difference now is that instead of paired equals false, we're going to use paired equals true, because this is indeed a paired test. Before, we were with independent samples t-tests, we were working with two groups that were independent of each other. But now our two groups are not independent. Now our two groups are paired. So for case 1 here, for row 1, this is the same test taker who scored 10.575 on the pretest and 10.53 on the post-test. So we say we're working with a paired sample here. Now you feed in your data, column by column, pretest and post-test, with paired equals true, into the ttest function. Call your variable something descriptive, like paired ttest statistic, and let's run this code. And now let's take a look at what we got. We can see that our p-value is extremely small, which means it is significant. This is called scientific notation, and it's used to write really big numbers or really small numbers. What this means is 4.283 times 10 to the negative 6th. So what we would do is move the decimal to the left 6 places. So you can see that this is a very small number, smaller than 0.000. These other values are also meaningful, and we would report them in our report if we were to write one. Next up, we're going to look at the effect size here. To calculate an effect size called D, or Cohen's d, for a paired samples t-test, you need to divide the mean difference by the standard deviation of the difference. This is very easy for the paired samples t-test. We very simply use the mean function, and we give it our column with the difference and divide it, and this is how we divide with the slash. We divide it by the standard deviation. This is the function for standard deviation, SD, and we give SD the same column. You save that to a variable, and then afterward you can look at the variable and get the value of your effect size, 1.42. Like I said, I'm going a little bit faster for this video than the previous video with independent samples t-test. Remember, you can always pause the video to catch up and type along with the notes. And I recommend going back and checking out the independent samples t-test videos to get a little bit more background. Lastly, the reason we've been saving all of these variables is so that we can have them in one place for later whenever we return to this. We would just go back through, execute our code really quick, and then we could come here, execute each of these, and we would see all of the information that we just accumulated. We would see all of the information that we just made in one place. You can see the data set, the descriptive statistics, the box plot here would show the Shapiro-Wilk normality test, the t-test that we ran, and our effect size all in one place. The result of this, since we know that our p-value is extremely small, we know that the difference between our two groups, in this case between a pre-test and a post-test of the same test takers, we know that the difference is significant. So if we come up and look at the means, look at the averages of the two groups, we can see that the pre-test was at 11.17 and the post-test was at 11.30. So the post-test was greater than the pre-test. So we can say that there was a statistically significant increase in test scores from a pre-test to a post-test as a result of an experiment, or having something to do with an experiment, about the effectiveness of recast as implicit corrective feedback. That was our intervention in the experiment.